Hello everyone, welcome back to my channel. I'm Bona. You're watching Math Mitra, your friendly math companion. In our previous session, we explained the fundamental theorem of arithmetic, which tells us that every composite number can be uniquely expressed as a product of its primes. We also looked at how to find LCM and HCF using prime factorization. In today's session, we are going to put these tools to work. We will be solving exercise 1.1 where we apply these concepts to find factors for the numbers. Let's dive into the question 1. Express each number as a product of its primes. See, we have to express this number as a product of its prime numbers. Okay. To get the factors of this number, use the factor tree method or by the division method. Here I am using the long division method. Start with the lowest prime number 2, 2 7s are 0, 2 3s are 2 5s are. Next use 5, 5 7s are and it is 7 1s. How we are going to write this 140? That as a product of all these prime numbers. 2 into 2 into 5 into 7 or 2 to the power 2 into 5 into 7. The second question is 156. Again use the division method. Start with 2. 2 7s are 14. 2 8s are 16. 2 3s are 6, 2 9s are. Next 3 1s are 3 3s are 9. Next 13 is a prime number, 13 1s. Again write that 156 as 2 into 2 into 3 into 13. Can write it as 2 to the power 2 into 3 into 13. The third question is 3825. Again use that long division method. See, the last digit of this number is 5. Start with the 5 itself. Okay. 5 7s are 35 becomes 32. 5 6 are 30 becomes 25. 5 5s are. Again the last digit is 5. Take down 5 again. 5 1s are 5. It is 26. 5 5s are 25 becomes 15. 5 3s. Next take down 3. 3 5s are 15. 3 1s are 3. Again you can divide it by 3. 3 1s are 3. 3 7s are 21. And 17 is a prime number, is 17. So write this 3825 as a product of all these prime numbers. That is 5 into 5 into 3 into 3 into 17. It is 5 squared into 3 squared into 70. Next, the fourth question is 5005 it is. Again get the factors by prime factorization method. See, the last digit is 5. Start with 5. 5 1s are 0, 0. Again 5 1s are. Next take down 7. 7 1s are 7. It becomes a 30. 7 4s are 28. It is a 21. Now 7 3s. Next take down 11. 11 1s are 11. Becomes 33. 11 3s are. Next it is 13 1s. Now how you are going to write these 5005? That as product of prime numbers. 11 into 30. The fifth question 7429. Again use the long division method. Start with the 17. 17 4s are 68. 17 3s are 51. 62 minus 51. Here you will get a 11 becomes 119. 17 sevens. Take down 19. 19 twos and next 19 threes. Next 23 is a prime number ones. Write this 7429 as a product of prime numbers. So this is how we expressed all the numbers as a product of their prime numbers. So the second main question is find the LCM and HCF of the following pairs of integers and verify that LCM into HCF is equals to product of those two numbers. The first question is 26 and 91. We will get the factors of these two integers by using factorization method. Start with 2. 2 ones are 2 threes. 13 is a prime number. 13 ones. Here I am writing 26 as a product of its primes. Again, take down 91. 7 ones are 7 threes are 13 ones. Again, I am writing this 91 as 7 into 30. HCF of 26 and 91. The lowest power of the common factor. See, the common factor is 13. So HCF is 13. LCM of those two numbers. Product of all the prime numbers and their greatest power. See, 2 into 7 into here we have to consider only single 13. So the product of all these numbers gives us 182. So now I got a HCF and also the LCM. Now let's verify the relation. What is that relation? See, the product of LCM and HCF is equals to the product of those two numbers. Here I am considering the LHS part of the relationship. What is that? LCM into HCF. I got LCM as 182 and HCF as 30. So the product gives us 2366. Now consider RHS part of the relation, that is product of those two numbers. So the first number is 26 here and the second number is 91. And the product gives us 2366. See, the LHS and RHS both are equal now. So therefore, hence the relation is verified. So the second question is 510 and 92. Again, we will get the factors for 510 and 92. Consider 510. 2 2s are 4. 2 5s are 2 5s. Start with 3. 3 8s are 24. 3 5s are 5. 5 1s are 7s are, and it is 17 ones. So write down 510 as a product of primes. 2 into 3 into 5 into. Next, get the factors for 92. Start with 2. 4s are 2 6. Again take down 2. 2 2s are 2 3s. So 23 is a prime number. 23 ones. So write down this 92 as 2 into 2 into 20. That is 2 to the power 2 into 20. So what is HCF? See, the lowest power of common factor. Common factor is 2 here and its lowest power is 1. LCM is product of all the prime factors involved in it and its greatest power. If we multiply all these numbers, we'll get 23,460. Now let's verify the relation. Here I am considering the LHS part of the relation, that is LCM into HCF. So I got LCM as 23,460 and HCF as 2. If we multiply these two, we'll get to 46,920. Now consider RHS part. Product of those two numbers. The first number is 510 and the second number is 92. If we multiply these two again, I'll get 46,920. See, the LHS and RHS parts both are equal. So therefore, hence relation is verified. So the third question is 336 and 55. Again, get the factors for 336. Start with 2. 2 ones are, 2 6 are, 2 8s are. And take down 2. 2 8s are, 2 4s are, 2 4s are, 2 2s are. Next consider 2. 2 2s are, 2 1s are. Take down 3. 3 7s are. Next 7 1s. So write down this 336 as product of all these primes. See, 2 to the power, here I am writing directly 2 to the power 4 into 3 into 7. Next, get the factors for 54. Start with 2. 2 2s are, 2 7s are. Next, take down 3. 3 9s are, 3 3s are, and next 3 1s. Add down that 54 as product of prime numbers 3 to the power 3. HCF is the lowest power of common factor. Here both the side we have 2, their lowest power. Next 3 and 3 to the power 3. We have to consider only 3. 2 into 3. So the HCF of those two numbers is 6. Next, LCM. The product of all the prime numbers and their greatest power. Here 2 to the power 4 into 3 to the power 3 into 7. That is 16 into 27 into 7. If I multiply all these numbers, I'll get 302. Let's verify the relationship. Consider the LHS part of the relationship, that is LCM into HCF. 3024 into HCF is 6. If we multiply these two, I'll get that as 18,144. Now consider the RHS part of the relation, that is A into B. If I multiply 336 to 54, then I'll get the number as 18,144. See, both LHS and RHS are equal. Hence, the relation is verified. The third question is find the LCM and HCF of the following integers by applying the prime factorization method. See, in the first question, the integers are 12, 15 and 21. We will get prime factors for all those three integers by using factorization method. First, I am taking 12. I am starting with the lowest prime number. 2 6s are, next 2 3s are, 3 1s. And here I am writing that 12 as 2 to the power 2 into 3. Next, I am considering 3 5s are, 5 1s. I am writing that 15 as product of primes, 3 into 5. Next is 21. Starting with the 3 7s are, 7 1s, and here I am writing that as 3 into 7. So what is HCF? HCF of the three numbers 12, 15, 21 is the lowest power of common factor. C. In all these three numbers, in their prime factors, 3 is common, isn't it? So HCF of the integers 12, 15 and 21 is 3. Next, LCM. LCM of the three integers, the product of all the prime factors and their greatest power. See, 2 to the power 2, 3, 5 and the 7. If I multiply all these prime numbers, I'll get that as 420. So the second question is, here we have to find the factors by the factorization method. But concentrate on the numbers. See, all the integers are prime numbers now, isn't it? See, here 17, it is a prime number, 23, 29, both are prime number only. So HCF of all the prime numbers is always equals to 1 and LCM of all the prime number is always equal to the product of the given prime numbers. Okay, so directly here I am writing the HCF of 17, 23 and 29, that as 1. Why? Because all the numbers are primes. Okay, always the HCF of the prime numbers is equals to 1. And what about the LCM? LCM of the given prime numbers is equals to the product of given primes. If I multiply all these numbers, I'll get that as 11,339. The third question is, see, the given integers are 8, 9 and 25. Again, get the factors for all these numbers by factorization method. For 8, start with the 2. 2 4s are, 2 2s are, 2 1s. So write this 8 as product of primes. Take down 9. Start with 3. 3 3s are 9. 3 1s are. Write down this 9 as 3 square. And next, consider 25. Start with 5. 5 5s are 5 1s. 25 is equals to 5. Now, so write down the HCF of all these three integers. See, none of the digit is common here. We'll write this 2 to the power 3 into 1 is 2 to the power 3. 3 to the power 2 into 1 is 3 to the power 2. 5 to the power 2 into the 1 is 5 to the power 2. So what is the HCF? HCF of the integers is 1 here. Now, what about the LCM? LCM of 8, 9, 25. That is the product of all the prime factors involved in it. Okay, if I multiply all these things, I'll get 1800 as the LCM of these three numbers. Fourth one, given that HCF of 306, 657 is equals to 9, find LCM of those two numbers. Here, to get the LCM of those two numbers, here we are using the relation. What is that relation? Product of HCF and LCM is equals to product of those two numbers. What are those two numbers here? See, they have given that one. See, this is our A and this is our B and this is our HCF. By substituting all these values, we can find the LCM. We know that the relation HCF into LCM is equals to A into B as given. So what is the value of A here? That is 306. And what is the value of B here? That is 657. What about HCF? HCF, that is given by 9. Now what we want? We want LCM na? So we just keep this LCM here only. A into B whole divided by HCF. Now you just substitute the values of A, B and HCF. That is 306 into 657 divided by 9 it is. 9 ones are 9 sevens are 63. Now it is 9 threes. If you multiply 306 into 73, you will get 22,338. So this is the LCM of these two numbers. So therefore, LCM of 306, 657 is equals to 22,338. So the fifth question is, check whether 6 to the power n can end with the digit 0 for any natural number n. What if the 6 to the power n is end with the digit 0? It must be divisible by 10, huh? Then if it divisible by 10 means its factors are what, 2 and 5? Okay, so it must contain both 2 and 5 as its prime factors. But what are the prime factors of 6? They are 2 and 3. Here I am writing this 6 to the power n as 2 into 3 whole to the power n, and that is 2 to the power n into 3 to the power n. See, in this prime factors, we don't have 5 as a factor, isn't it? So the prime factorization of 6 to the power n contains only 2 and 3 as its primes. It does not contain any 5 as a factor. So by the fundamental theorem of arithmetic, 6 to the power n cannot end with the digit 0 for any natural number. The sixth question is, explain why this and these are composite numbers. To tackle this question, first we have to know the definition of composite number. It is nothing but the number which has more than 2 factors. First, we will express these two numbers as the product of their prime numbers. Okay, so the first number is 7 into 11 into 13 plus 30. Okay, so 13 is common. Take down 13. 7 into 11 plus 1. 13. In bracket it is 7 into 11, that is 77 plus 1. 13 into 77 plus 1 is 78. Okay. Again, get the factors for 78. Here 13 is prime number. Again, get the factors for 78 by prime factorization method. Start with 2. 2 3s are 9s are. Next 3 1s are, 3 3s are, and 13 is a prime. Now 13 into, here I am writing this is 78 as a product of these primes. 2 into 3 into 13. Here I am writing it properly. 2 into 3 into, here we have 2 times 13. That, yes. So we have expressed the given number as the product of primes, isn't it? So this is what your composite number. Next we will check out for the second number, that is 7 into 6 into so the second number is this. See, take down 5 common. So the remaining is plus 1. If I multiply all these digits, I'll get that as 1008 plus, again it is 5 into 1009. So I have expressed this number as a product of primes. These two numbers both are composite numbers because they have many factors other than 1. So now the last question of this exercise. There is a circular path around a sports field. Sonia takes 18 minutes to drive one round of the field while Ravi takes 12 minutes. Suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting? To tackle this one, see, imagine a circular field. Sonia and Ravi are standing at the starting point here. Sonia and Ravi. Sonia is a bit slower. She takes 18 minutes to come back here. Whereas Ravi is faster. He takes only 12 minutes. If they start together, Ravi will finish a lap while Sonia is still halfway through, isn't it? To find out when they both land on this exact spot at the same time again, we need a number that is a multiple of both 12 and 18. Specifically, what we have to find? We have to find the LCM, least common multiple. For that one, see, this is given that Sonia takes 18 minutes, whereas Ravi takes 12 minutes. So, after how many minutes they'll meet? So, for that one, we have to find what the LCM of 12 and 18. So, let's find the factors for 12 here. 2 6 2 3 3. So, 12 is equals to 2 square into. Next, similarly get the factors for 18. Start with 2. 2 9s, 3 3s, 3 1s. I am writing 18 as 2 into 3 square. So, what is the LCM of 12 and 18? 2 square into 3 square. It is 4 into 9, which is 36. After 36 minutes, they will meet at the starting point. So, this is all about today's session. In next session, we will discuss about the concept called irrational numbers. If you found this session helpful, please subscribe to my channel so that you don't miss our upcoming videos. And also, if you have any doubts regarding today's session, just leave a comment below so that I'll clarify them in my next class. See you then.